All right, so going over our skier problem very quick. For part A, we're drawing the free body diagram, and just a reminder sort of what the hill looks like as we've got our angle theta here. So you can imagine your skier. All right, so our dot t is here. The free body diagram, remember, a free body diagram is just supposed to show all the individual forces acting on the object. There's only 3 forces acting on our skier. So we've got a force of gravity, we have a normal force, and we have a force of friction. Which will be kinetic friction in this case. Or I guess it's sort of the weird friction that's the negative kV. So there's some sort of resistive friction force here. And you can label these whatever you want. So remember, the force of gravity is the same as weight. So like you could call this mg if you wanted to. You'll notice this does not involve the little subcomponents. So finding like the x and y component of the force of gravity, that is something we do during problem solving, but the free body diagram itself just shows the actual forces. For part B, we want to find our differential equation, which basically means we're going to need an equation with acceleration and velocity in it, so we can use the fact that the derivative of the acceleration with respect to time is... the derivative of the velocity with respect to time is the acceleration. So if we get an expression with acceleration, we can turn it into dv dt and get our differential equation. And so to do that, might help to utilize our equation here. So I'm going to kind of add on to this diagram, but you would normally want to show this work separately. So FGY is going to be, that's theta, so that's going to be mg cosine theta. FGX here is going to be mg sine theta. So Fn is going to be equal to our FGY, which is mg cosine theta. And the force of friction we know is equal to negative, the magnitude is BV. So remember, our force of friction as a vector points in the opposite direction as the velocity, and so if we write it as vectors, which the way that they've shown it's a vector on the AP test is they put this in bold to indicate it was a vector instead of putting a little vector sign over it. That's fine. If we're just writing the magnitude, though, we've already drawn the arrow in the opposite direction because, of course, our skier is going, down the hill, right? And so we've got our force of friction going in the opposite direction, so its magnitude is just BV. Everything cancels in the y direction, so in the x direction, our net force just winds up being FGX minus the force of friction, or we could write it as vectors. The net force is going to be the sum of the x component plus the force of friction. Either way you do it, you're going to wind up with, of course, your net force is your mass times your acceleration, which I think they use capital M for the mass of the skier in this problem. FGX is going to be mg sine theta, and the force of friction, so either when we do it in our vector form here, this becomes this negative BV term, right? And so we have everything in our vector form. Or if you did it in this form, you would actually wind up getting the right answer too, because you would get the net force is mass times acceleration, FGX, minus the magnitude, which is BV. If you don't do it in the vector form, you just want to check and make sure that everything still works out. So if we want to wind up with, a positive acceleration because our net force is in the positive direction, this would be implying that mg sine theta has to be bigger than BV, which is true over the course of the problem. And so this is going to be the expression we use. We want to turn that into a differential equation. And so I guess at heart, all we really need to do is change the acceleration to dv dt. And so you could just do m dv dt equals mg sine theta minus bv. That's fine. Yeah, but we could also, if you wanted to actually like have it solved for this, you could divide the m out. So if you wanted to leave it like that, that's fine. If you wanted to divide the m through, we could, have something like that, and then you just have a straight dv dt. That's fine too. Any sort of rearranged, mathematically true version of this is absolutely fine. For the terminal speed, remember the terminal speed occurs where our net force is 0. And so remember our net force was equal to, what did we come up with on the last page? mg sine theta minus bv. And of course that has to be 0 if we are at our terminal speed. And so we're going to get mg sine theta equals bv, terminal v. And so the terminal speed is going to be mg sine theta over b. And that should be one of our limits. When we solve our differential equation, as time goes to infinity, we should get this as our terminal speed or terminal velocity. The magnitude is the terminal speed. The terminal velocity, if we have the positive direction going down the hill, this should all wind up being positive, which makes sense because we would expect our terminal velocity to be forward down the hill. For part D, we actually want to find an expression for the velocity as a function of time. So we're going to have to solve our differential equation. So I'll switch to a new sheet to do that. So what do we come up with? We know that dv dt equals g sine theta minus bv over m. So I want to solve this for v. I know I've got v in two places here, so the first thing I'll do is combine my like terms, get all my v terms on the left side, which requires me to divide out by this entire thing because I can't solve dv plus bv over m. I need to get it to be in the 1 over u form, and so we'll get dv over g sine theta minus bv over m equals dt. And now we have our like terms together, we got all the v's together, and so we can just integrate this. And this is, again, where you can do this in all sorts of different ways. I liked using the definite integral. I think in the answer key to this one, they show the indefinite form where you get a plus c and you solve for the constant, and that's absolutely fine. But I'll do it with the definite form because I like that a little bit more. So our initial velocity was 0 because it says we started at rest, and we're just trying to figure out, so we're going to go up to some final velocity. And our initial time is 0. We're going to go up to time t. So when we integrate this, we're going to use a u substitution here. So u is going to be g sine theta minus bv over m. That means du, this is a constant, so that goes away, is going to be negative, so these are all constants, b over m. V's are only variables, so when we take the derivative, that'll be the only thing we actually wind up with a derivative term on. I want to know what dv is, and so if this is true, that must mean that dv is equal to negative m over b du. Okay, so this term, if we do our u substitution, is going to be, so dv we know is negative m over b du divided by u. And then when we integrate, we're no longer doing it with respect to v, but with respect to u, but we use these values for v when setting our new limits. So this is going to be g sine theta minus b times, so v is 0 for this one. And then up here, u is g sine theta minus b, and then for v, it's just v over m, equals the integral of dt, which is just, of course, t, which we evaluate from 0 to t. So this term is a little ugly, so we'll go ahead and solve this. So I got a constant. I can move that out to the front. This down here is going to go away, so this is just g sine theta. And so we'll clean that up. So that's going to be negative m over b times the integral g sine theta minus bv over m. And of course, so you know from calculus class, if you don't like changing the limits of integration like this, you are also certainly welcome to, instead of having, the integral of 1 over u du, and then just leaving it like this, you're allowed to do the integral and then replace the u in here with the g sine theta minus bv over m, and that's fine too. All right, so this is going to be, so t evaluated from 0 to t is just t minus 0, so that's easy. All right, so this is going to be negative m over b times the natural log of u, absolute value of u, evaluated between our two limits. And again, the other way to write this is instead of doing it this way, you replace u with the g sine theta minus bv over m, and then your limits of integration are what we originally had, 0 and v. It's mathematically going to do the same thing. If we look at our u term, so remember u here is, where'd that page go? G sine theta minus bv over m. And we might recognize that that is our acceleration. So remember our net force was this, mg sine theta minus bv. And so if we divide that by m, we are getting this. And so this is always going to wind up being positive. And so when we are taking the absolute value of u, because over the course of our problem, for the times we're looking at the skier, u is always positive. We don't need to worry about the absolute value. We can just, just take the natural log of u. That's fine. So this is going to be negative m over b times the natural log of g sine theta minus bv over m minus the natural log of g sine theta equals t. And now it's just a math problem, so I want to use my log rule here. So that's going to become negative m over b natural log g sine theta minus bv over m divided by g sine theta equals t. I'll get my natural log term by itself and sort of simplify this. And so you get the natural log of, so g sine theta over g sine theta is 1 minus bv over mg sine theta. Move this constant over to here, so we get negative bt over m. And then, we take e to this side, and so those cancel out. And so we're going to get 1 minus bv over mg sine theta equals e to the negative bt over m. We, of course, want to solve for v right there. That's what we want. And so we'll start isolating that term. So bv over mg sine theta equals, so 1 minus e to the negative bt over m. And so that's going to give us then v equals mg sine theta over b times 1 minus e to the negative bt over m, which let's check and see if that's right. Yes, that appears to be correct. And then for the last part, We need to make a sketch of the acceleration as a function of time. And so we know, of course, the problem that is occurring is that, as the skier goes faster and faster and faster, the friction gets larger and larger and larger until eventually we reach terminal speed, which is where we're no longer accelerating. So we know as time approaches infinity, we're going to asymptotically approach 0. And then we need the initial acceleration. So remember, for our skier, where'd that diagram go? Our initial gone. So we got so remember we had the net force was the FGX term minus the force of friction, so that was MA equals, that would be what, mg sine theta minus BV. But of course, at time 0, our initial velocity was 0, and so this term just goes away. And so MA is mg sine theta, and so the acceleration, our initial acceleration when we start going down the hill is just g sine theta. So we know our plot needs to start at g sine theta at time 0. So we start with an acceleration of g sine theta. We're approaching our terminal speed, terminal velocity, and so our acceleration is eventually going to go to 0 when we have finally reached that, because we no longer accelerate. And so our graph must be the graph that does that. That starts at g sine theta and then just asymptotically approaches an acceleration of 0. And that is a horrible line, but that is what the shape should look like.